In section 3.2, we're looking at the derivative as a function, and we're going to start with the graphs of the derivative. So we call the derivative function f prime. It's the derivative because it is derived from f. And we've already talked about it algebraically, so now we're going to also look at deriving it graphically. The first thing we're going to look for is intervals over which the function has a constant slope. I'm going to switch to a screen here that has a Desmos graph. It's also linked to in your notes. So in this particular graph, the slope is constant at all points. On the first segment, the slope is a constant positive because it's a linear segment. The slope of this piece is, looks like 1. It's got a constant slope here where it's 1. It has a constant slope up here again where it's all 0. And a constant slope down here of negative 1. So any segment of a graph that is steady or linear will have a constant slope. I'm going to write that on the previous page. Any segment that is linear is going to have a constant slope. It doesn't matter if it's linear increasing, decreasing, or linear horizontal. All of those will have constant slopes. The next thing I want to get information from the graph of a function is for any locations where the function has a slope of 0. I want to be cautious of abrupt changes in direction. I'm going to look back at my previous graph again. When the slope is 0, that is when I have a horizontal segment or a horizontal tangent. So just to add another picture here, if I look at the graph of a parabola, like y equals negative x squared plus 2, some kind of parabola, anytime that you have a soft turnaround point right there, the tangent is going to be horizontal. If I just bump that up to 3, you can see that the line right here that has 0 slope is going to be tangent to that graph. So we're going to be looking for those soft turnaround points for a place where the graph has a 0 slope. Now, the previous page also said to beware of abrupt changes in direction. So just for contrast, if I look at the graph of, say, y equals the absolute value of x, and to make it look like the other graphs, I can reflect it, maybe add it up a little bit. So this graph is sharp, and because it is sharp, it's not going to have a tangent of 0 right here. Instead, it's going to be, looks like the slope on this part is positive 1, the slope on this part is negative 1, so its derivative is going to be undefined at this point, since it's going to have two different limits on the left side and the right side. So we want to really be cautious of those sharp points. I'll go back to the previous page and summarize. Finally, we also want to look for intervals over which the function has always positive slopes, as well as intervals over which it has always negative slopes. We can see that a little bit in this first graph. This segment right here is always positive, this segment right here is always negative. But let's look at a little more interesting picture in another graph to see some sections of always positive and always negative. Okay, so in this graph, first of all, just looking at the f of x picture, you can see that we are increasing. So this derivative is always going to be positive. And so you also see that the derivative right here is always positive. Then you have a place where you have a horizontal tangent, so the slope is 0. You see the value of the derivative is 0. Then you can see that you're a decreasing function, so the value of the derivative is negative. It hits 0 down here again, so your derivative hits 0. And then after that spot, we go positive, and so the derivative values are all positive. Those are some of the things we're going to be looking at. So the function will be increasing wherever the derivative is positive, and the function is decreasing wherever the derivative is negative. Also just keeping in mind that it can change from increasing and decreasing. The derivative can change from positive to negative whenever the slope of the function is going through an extrema, so it's either a rounded or pointed extrema, or has an asymptote, so it can be doing different things on either sides of an extrema or an asymptote. So in the next couple of examples, we're going to be using the locations of those intervals from those 3 parts above to be sketching the derivative without knowing the equation, just from the picture. Okay, so for this first one right here, again, I have some graphs and Desmos to help me out. In this first one, I see the graph of this first function. I want to look at its derivative. Since this function is linear and it is decreasing all the way, should have a constant slope, and that slope should be a negative number. I can see that that's about what that slope would look like. It appears to be about -1, so I've got a -1 value for my slope. And if you look back at the graph we have here, you see the same thing. The slope is -1 for this line. It's going to have a constant slope at -1, so we would draw -1 through that line right there. We'll just draw the slope value being -1 to draw the derivative. If we look at part B, this is an absolute value graph, but it's piecewise linear, which means it seems to have a slope that is negative and then a slope that is positive. The first negative slope looks like -2, the second positive slope looks like +2, so if I flip over and look at the graph of the derivative, it's going to look like always at -2, always at +2. Those open circles didn't line up correctly. They were supposed to be right here at the end of these points. I'll have to fix that. Okay, there we go. That's what the graph should look like. It's going to be a value of -2 all the way across the bottom, +2 all the way across the top. Open circles right there because the derivative is not defined at this point. It couldn't be defined at this point because the value from the left is different from the value from the right, so that limit doesn't exist. Again, the derivative is the limit. If the limit doesn't exist, it won't have a function value for the derivative. The next graph, this is a parabolic shape, so let's explore what this looks like for its derivative. The function itself is increasing until you reach the vertex where the slope is going to be 0, and then it is decreasing. So it should have positive values of slope. Now these values are not constant. They have larger slopes and then smaller slopes. So these positive values are going to start off being larger positive values, then come down and be smaller positive values. So I'll have larger positive values down to smaller positive values down to 0, and then smaller negative values down to larger negative values. So the graph is going to look like a line. Larger positive values down to smaller positive values, 0, and then where I have the vertex, I have a slope of 0, and then I have low negative values, and then eventually the slope gets steeper and I have low or high negative values. So that would be the derivative for part C. So go back and look at our notes again for the graph of part D. Okay, so here, the graph of part D, these values of slope are going to be very, very steep originally, and then they're going to be flattening out and getting lower and lower and lower. So that is going to look like very, very steep. So these are all positive, so all my values will be positive. I'll have very large values and then very small values. So very large positive values swing down to very, very small positive values. So I will have a graph like this for its derivative. Very high values swing down to very, very low values of positive integers. Positive numbers, I meant to say, not integers, positive real numbers. And if you play along with the demo here a little bit more, you can watch those slopes if you play with the slider right here in the tangent line. So you can watch the values of slope. Again, down here they're very, very steep, and then they're going to shallow, 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 get to those low slope values